Hello, everyone. Thank you very much for joining this webinar today. My name is Amir. I'm one of the founders of AOMS Technologies. Today, I'll be talking about the new technology trends for concrete monitoring based on the maturity method. Please feel free to post your questions under Q&A or in the chat box. I'll make sure that we'll have enough time at the end of this webinar to go through all the questions and have a productive conversation together about this concept and the technology trends around this technology. So as the agenda, I'll be first touching base on the concept of the maturity, what it means and how it works. The concrete calibration associated with the maturity method. I'll talk about a couple of ideas around the maturity and strength functions for different type of design mixes and how maturity can be compared versus the cylindrical test or the concrete samples in general for testing the strength of the concrete. And then I'll be talking about concrete monitoring and the fact that concrete monitoring is not just about the maturity and the concrete sensors, but also how the weather data can affect the curation of the concrete, the forming zone, the matchboxes. There are all these parameters out there that can contribute to proper curation of concrete. And finally, I will go through a few case studies. So a quick overview about our company. We are based out of Toronto, Canada, and we offer industrial IoT solutions for harsh environments and monitoring harsh environments for industrial applications. And we are very much focused on digitization of the construction job sites. And concrete sensor is one of our flagship products, but we are not limited to this. We have this idea of around providing different type of solutions that can, again, contribute to the productivity at the construction job sites. But let's talk about the concrete monitoring. And the best place I would say to start is the cylinders or the concrete samples. We're all familiar with the cylinders. We know that they have been around for many decades to provide information about the quality of the concrete and also the strength of the concrete. So there have been always debates around the accuracy around the cylinders and how they can be a good representation of the slabs or the mass concrete pours. So first of all, we all know that the pace of curation in the cylinders can be different than the concrete slabs. And it is all tied with the fact that we are dealing with a smaller mass of concrete inside the cylinders or the cubes compared to the mass concrete. And for those reasons, it is known that it can happen that the pace of curation of concrete, specifically in the initial days, could be different compared to the mass concrete. Also, cylinders are being cured in the lab environment, and based on the ASTM standard, we usually put them at 23, 24, 25 degrees C. And again, that would create a different environment compared to the mass concrete, where the temperature can reach to 50, 60, 70. Sometimes I've seen cases like in Hong Kong that it can get to temperatures beyond 90, 100 degrees C for the special design mix that are used. So again, that would add to the uncertainty around how the cylinders could be a representation of the mass concrete. It's a time-consuming process. It's prone to error during the sample preparation and testing. We need to grind the cylinders before we crush them, so it can introduce some local stress during the sample preparation and also during the transportation. And with cylinders or with these samples, we don't have continuous data about our concrete, and we don't have real-time visibility into the temperature or strength of our concrete pour for the casting place. So for those reasons, ASTM proposed a new methodology to understand the in-situ strength of the concrete, and it is called the maturity method. So it is a non-destructive approach. It is mainly used for those type of concrete that would generate heat, that they would undergo exothermic reactions. And this methodology basically talks about that how we can correlate the heat generated during the curation of the concrete, how we can correlate it to the strength achievement in the concrete. So it is a methodology that is widely accepted in North America by more than 29 states. They're accepting the maturity method. They are using it for their projects. And again, there are the European standards that also in support of this methodology. But what is maturity? So I'm going to just read this blurb from the standard, and then I'll try to deep dive into it a bit further. Maturity is a technique for estimating concrete strength that is based on the assumption that samples of a given concrete mixture attain equal strength if they attain equal values of the maturity index, regardless of volume, regardless of the volume. So basically, if two different samples of the same design mix, one small, one big, if both of them reach the same or attain the same maturity numbers, it is an indication that both of them could have reached the same strength. So it's all about the fact that how the maturity can be correlated to the strength. So and how the temperature during the heat generation inside the concrete can be correlated to the strength. So, and then there is a maturity curve that could be the signature of your concrete. The maturity curve, that is a correlation between the maturity development in the concrete and the strength development in the concrete. And this could be unique to each design mix. The idea is that this curve would, again, regardless of where you are curing your concrete or how you are curing your concrete or what the sample size we are looking at here right now, this maturity curve could be applied for that design mix. Now the question is that how the maturity curve could be created, how the maturity curve for each design mix could be prepared so we can use it for estimation of in-situ strength of the concrete. So in order to prepare this calibration profile or the maturity curve, there is a process that is introduced by ASTM, and it's a calibration process. We need to calibrate our concrete. And based on this process, we need to have a good number of samples. ASTM is proposing 17, but I'll say that this is not something set in stone. Based on the different design mixes, we can make changes. But based on this process, for the calibration of the concrete, we prepare 15 cylinders or 15 samples, either cylinder or cube. And then we have temperature sensor in 2 of the cylinders. So based on the temperature data that are being collected from these cylinders, we are able to understand the maturity development or maturity attainment in our sample versus time. Then we have other 15 samples that we break them on certain intervals. So it is a conventional concrete. It cures in 28 days. ASTM is proposing that we break the cylinders on day 1, day 3, day 7, day 14, and day 28. However, as I mentioned, if you're dealing with high area strength concrete, or we are dealing with a UHPC, like ultra high performance concrete, that the curation is faster. And you can expect the concrete to reach 70-75% of the ultimate strength in 24 hours or in 48 hours. Maybe in those cases, you wanna kind of crunch, you wanna squeeze these samples into a break schedule of every 4 hours, every 6 hours, every 10 hours, depending on the design mix. But at the end of the day, we need to have minimum 5 data points to be able to create the calibration profile. And once we have the strength data versus time, now I have 2 curves. I have maturity versus time based on the temperature data that I have been reading from the cylinders, and I have a strength data based on the crush of these cylinders. Now I can have a beautiful curve here for the maturity curve, which is like magic. So we have M1, S1, M2, S2, and so on and so forth. And it would give me my maturity curve. That would become, again, the signature of my design mix. And now, when I am reading the temperature from the design mix, from the casting place, I am able to, based on the temperature data, calculate the maturity, and then fit the maturity into this curve, and then understand what the strength of the concrete is in real time. Now the question is that, so different design mixes would have, again, different behavior. So that we cannot have one simple model to be able to use it to understand the maturity curve. So depending on the type of the design mix, for maturity equation, we have, the most common equations that are, or the models that are used are Nersol equation and Arrhenius equation, or equivalent H method. So the Nersol equation is used for the concrete temperature that is typically, they don't typically exceed 50 degrees C within the first 2 hours, or about 100 degrees C within the first 6 hours after a start of mixing. That's general. Generally it is the case. And then if you're using Nersol equation for maturity, then the strength maturity function that we could use, again, could vary. Could be, the most common one is the Plowman function, which is a logarithmic type of equation to correlate a strength with maturity. But I have seen cases out there that there are companies, or there are different, like I've seen in ready-mix suppliers, that they have come up with their own equation for the best approach for the strength maturity function, like quadratic approach or a different type of logarithmic function here. And if you're using Arrhenius equation, so then we have three options: linear hyperbolic function, parabolic hyperbolic function, or the exponential function, which is also known as Peterson. So in general, we need to, based on the maturity data and based on the strength data, we need to be able to understand which maturity function and which strength maturity function would be the best representation of our design mix. And it is correlated with mainly with three parameters: the regression that we do here, like the R-squared value, the standard deviation, and also we need to also bring some knowledge that I have seen cases that, like, the standard deviation is good. I've seen cases that the R-squared value is very high, but at the end of the day, this doesn't make sense, because at earlier stages, that the concrete is still very, very soft. It's not cured, but it shows some strength data. So this is important to bring some knowledge and wisdom into understanding of which function would work better for our design mix. And I have some examples here. Like for the high earlier strength concrete, usually the Arrhenius function, as I mentioned, and the linear hyperbolic or hyperbolic parabolic equation would work better. And you can see that for the initial days or initial hours, there is not that much of a strength development, but suddenly the strength development happens. So we have a very steep slope here that the concrete gets cured very fast. And but we have seen this one, like for a conventional concrete, usually the case is that the slope is not that steep. It just takes a while. Like for example, the 7-day rule that usually takes 5, 6, 7 days to get to 70% of the strength. The other thing that I wanted to also show here is that, again, the curation or the strength development depending on the dimension of the pore could be different. Like in the core of the concrete versus the surface of the concrete, we can see that because of the pace of curation, the strength development versus time could be different. So it is very important, again, when we are using the maturity method, to make sure that we have the sensors at different locations, at the surface, at the corner, or maybe in the core of the concrete, to understand how the strength is being developed at different parts of the concrete. And usually we have to take a conservative approach. You want to have the sensors, maybe if you want to take conservative approach, you want to put the sensors closer to the end of the pore, where the curation is slower, or basically we are talking about the fresh concrete and closer to the surface. So this is another example that, again, it was very interesting about the fact that the cylinders specifically for earlier strength concrete, they don't show the real pace of curation. That we had a case that it was our clients were using a high earlier strength concrete. We did the calibration. We realized that the best maturity curve for them is the parabolic hyperbolic equation, and it was a concrete that they were stripping on a 3-day cycle. And then we proved to them that actually the 70% of the strength is achieved in less than 10 hours. So they can potentially save about 2 days per that pour, and which is a huge time saving using the maturity method compared to the cylinders. And you may, I mean, this question always, I mean, I'm always seeing that people ask me this question, that why, how we can trust the maturity and how maturity can be compared with the cylindrical test. So we actually did a quick mock-up trial with one of our clients, and together we decided to prepare a small section to pour the concrete, and then they used our technology for maturity method, and then they prepared this typical cylinders for testing, and they decided to do the core test as the benchmark. We all know that core test is a relatively accurate method compared to the other conventional in-situ strength monitoring practices out there. So we decided to use the core test as the benchmark, and it was quite interesting. Like on day 5, the brake test was showing 56 MPa, whereas the core test was about 76 MPa. 20 MPa difference in the data, which is a significant difference again in the pace of curation. And again, you can see that the maturity method was on par with the core test. On day 7, the brake test was 70 MPa, core was 80, and the maturity was 79. There's an interesting factor here to consider, is that on day 5, the difference between brake test and core test was 20 MPa, and on day 7, it was 10. So as you can see, the pace of curation again is very different in the initial stages of the curing. But when we get closer to that 28-day of cycle for curation of concrete, they become closer and closer to each other. However, we all know that the initial stages of the concrete curation is more important to us, because it helps us make a decision on when to strip the formwork and how we can help with the productivity and advance the schedule. So potentially, if our client started using this technology because the maturity adopted the maturity method, and the reason for that is that the maturity was able to help them save about 3 days based on their design mix for form stripping. The other value that I kind of talked about earlier is the fact that cylinders do not provide real-time data, and they do not give you continuous data. So we had another case study where we prepared a small sample, a very small sample of the concrete, and we used the maturity method, and at the same time, we were kind of breaking cylinders from that small mock-up trial. So this blue curve that we see is the maturity. Basically, is the data about the strength of the concrete that was calculated based on the maturity method. Here is the cylindrical test data. They were kind of overlapping with each other because it was a small sample, and they were kind of being cured under the same conditions. And then, as you can see, when we were looking at the data, 70% of 30 MPa concrete that we were using was actually achieved on day 3. However, because on a typical schedule, they were breaking cylinders on day 1, day 2, day 5, and then later on, they had a day, they had a day 7 and day 14. But based on their break schedule, the actual time of formwork removal was on day 5, whereas the 70% of 30 MPa was actually achieved on day 3. So this is another value of being able to have real-time access to the data, even if the pace of curation in our samples, or basically in the casting place and our cylinders, even if the pace of curation is similar, but still using this technology to be able to have continuous access to the data is also very important in making sure that we can make the right decision at the right time. Now, speaking about the technologies out there, so LumiCon is one of the technologies that that can be used for all different type of concrete pours, concrete placement, both for quality perspective. We all know that the concrete sensors are also important to make sure that the concrete does not overheat. I mean, the temperature differential is there between the core and surface. It doesn't go beyond 19 degrees C or 35 degrees Fahrenheit. You want to make sure that, again, the differential between the surface temperature of your concrete and the ambient temperature is not beyond like 15, 20 degrees C, within that range. So these are for quality, but also this technology, as long as it's reliable and it provides remote and real-time access to the data, it can help with the understanding the maturity and the strength of the concrete. And this is the architecture that we are providing to our clients. First of all, we have a very interesting approach into monitoring the concrete, which is doing monitoring through a distributed fashion. As I mentioned, I mean, monitoring the curation of the concrete and the quality is important to be done at different locations. You don't want to use only, for example, one sensor at one corner, or just put one sensor at the core of the concrete. Again, if you're dealing with the concretes that are thicker than 8-inch, you want to make sure that you have sensors at different locations for monitoring purposes. And that's why a distributed sensing fashion can help to have just a single ruggedized armored wire that can have more than 30 sensors on it, and then you can use it at different locations for monitoring. And then these cables that are, I mean, based on our LumiSense Pro, would be connected to a transmitter node that is battery powered. And depending on the job site conditions, we can have two different architectures to be able to send the data to the cloud. So either if there's a cellular coverage at the job site, our Luminode devices or Luminode Plus would be able to send the data directly to the cloud through the cellular network. Or if it is a remote site and we don't have cellular coverage, then we are able to send the data through wireless protocols to a gateway. And the gateway can be sitting next to the trailer, even like a couple of 100 meters or even a few kilometers away from the job site, where, again, the node are able to wirelessly transmit the data to the gateway. And from the gateway, we can connect it to the wired internet or Wi-Fi that is typically available inside the trailer to be able to send the data to the cloud. So it's a very ruggedized and armored design, very easy to install, very easy to use. Basically, what you need to do is to just plug the cable to the node. It would wake up automatically, start sending the data to the cloud. And obviously, after the monitoring is done, you can cut the cable. You can see how armored and ruggedized the cable is. Once you cut it flush to the surface of the concrete, then you can use the node for the next bore. So it's a device that can be used for, I mean, with the lifetime of more than 5 up to 10 years. You can use it continuously over multiple projects. So it is also very important not just to be collecting the data, but also being able to analyze the data and provide the right information at the right interface to your client. So we have a very sophisticated mobile application and online dashboard under the LumiCon system that through this technology and through this software, we are able to provide the real-time data about the temperature, about the strength. I mean, we have the option of customizing the transmission rate of the data depending on different type of projects. And so you can see the real-time data when the data is being transmitted to the cloud. Temperature, strength, we can see the graphs, you can set alarms, obviously. We have a very sophisticated feature with respect to report generation. I mean, the customized report generation feature that we have on the software is very much designed based on the requirements from the DOTs, MTOs, to be able to, again, help our clients have an easy process of sharing the data with their colleagues or the owners of the project. So in summary, it's a truly remote monitoring solution. You don't need to go to the job site to collect the data. It provides a very, very reliable connectivity. And the important thing here is that our Luminodes are also data loggers. So with that aspect, you never worry about losing the data, because at the end of the day, even if the connectivity is down, the data is available to be downloaded from the Luminodes. Very advanced precision. I mean, here we are not using thermocouples, we are not using thermistors. We believe in using a very advanced sensing technology here because concrete is important and maturity calculation is critical. So if you are dealing with a sensor product that has a low accuracy, like if you're using thermocouples or thermistors, you may end up with a high accumulated error for the calculation of the strength. For comparison, thermocouples have an accuracy of between 2 to 3 degrees C. Thermistors have an accuracy of plus minus 1 degree C. We are using type of sensors that would provide an accuracy of plus minus 0.1 degree C. So this would provide a high level of confidence about the accuracy of the calculations that we do for maturity and strength, and also for temperature differentials and the quality. And we can cover a wide range. Our sensors are able to cover somewhere between minus 30 to plus 125 degrees C. As I mentioned, it's a very rugged and dependable product, and the nodes are rechargeable, reusable, and we provide the standard configuration for the cables for quality and maturity. However, this cable can be fully customized based on the requirements of the project and the port dimensions. So, overall, this is a technology that can both help with the quality assurance and also with the schedule optimization. There are two main aspects, but again, based on the maturity method, you are able to significantly add to the productivity at the job site. The other thing that I wanted to cover today is the fact that these days we hear a lot about the concrete sensors and the maturity method, but something we need to consider here is that the curation of the concrete is not just about the maturity. Curation of the concrete is also important when it comes to the casting place projects, and when we are dealing with different weather conditions. So having a weather box, having a weather station that can help monitor the temperature, ambient temperature, humidity, wind, smoke. These are all also important, first for the safe operation at the job site, and second of all, the local ambient temperature and relative humidity or precipitation, they all affect the curation of our concrete. So monitoring the above of the concrete and also underneath the concrete is important, specifically like for the high-rise project when we are in the forming zones and we are using heaters. So monitoring the temperature under the forming zone and make sure that the heater is doing the job is important. And again, there are other byproducts when we are using the heaters, again, for the safe operation at the job site, like hazardous gases like CO and H2S that come out of this. So this is important to have a kind of a fully packaged solution to ensure the proper curation of the concrete at the job site. And this can be now also tied with the Matchbox. Matchbox, it's the other product that we provide to help our clients. Is the product that simulate the same temperature environment of your concrete inside the cure box. So basically the cylinders are going to be exposed to a similar environment or the similar temperature conditions. So to ensure the curation of those cylinders are close to the curation of the mass concrete. And we understand that there's an ASTM standard out there that requires curation of the cylinders at like 23, 25 degrees C. This is obviously very, very important. But at the same time, if you want to still use the cylinders for form stripping, so the Matchbox is something that can add value, and that could help to have again kind of field cure environment or mass concrete or the concrete slab curation environment for our cylinders. I have a few case studies to go through. So one example is the water river dam project that we are working on right now. And this is an interesting project site, a very complicated site, and no cellular coverage. And in that project site, there was a trailer which was about 2 to 3 kilometers away from the water dam site, but they had wired internet available. They had fiber network. And we were able to boost the signals about 2.5 kilometers away from the water dam site to the trailers to provide remote access to the data. So the crew do not have to commute to the job site, like specifically in the winter time, to collect the data. They are able to remotely see the data from their offices and make the proper decision. So that's a very interesting example on how we can customize these solutions for difficult and challenging sites as well. This is another project where, I mean, it was a passenger terminal. The sensors were installed, and in the massive concrete placement, and I mean, we had about 120 sensors installed for this pour, and it was a tunnel under the taxiway to connect two passenger terminals to each other, and it was a beautiful project we did there with flawless and seamless data streaming to the cloud with all the sensors. And the other one is about so that's something that helped with the productivity and also with the quality assurance. And we had one sensor actually sticking out from the concrete for local ambient temperature reading, but our Lumi nodes are also able to read the local ambient temperature on top of the surface of the concrete. So you can see that, for example, on this particular day, the temperature was going above 100 degrees Fahrenheit. So these are the anomalies that you want to consider during the curation of your concrete. These are some other examples for a few high-rise projects like that, how our clients are being able to save time with respect to the pour schedule, and also again with respect to productivity. Like this project, 45 days return to schedule by optimized form stripping. This is another project that our clients were able to strip the formwork 2 days earlier per pour. And this is another example for monitoring the forming zone that I wanted to talk about here. I mean, we had the sensors close to the heater and also in the concrete footings. And during the weekend, this is the value being able to have real-time and remote access to the data. During the weekend, no one was at the job site, and they got the notification from the system that the temperature has dropped. And then they had someone they sent someone to this job site, and they realized that one of the heaters had run out of fuel. So with this technology, I mean, we were able to prevent the concrete rework. So that's pretty much it. And so I want to just open the floor and basically provide the chance to have some Q&A here, and please feel free to post your questions or comments in the chat box or in the Q&A box here. I'll be happy to discuss it with you.